Hello and welcome to another AP Physics 1 review video. This is the last video in the series, and today we're going to be discussing the ideas of electrostatics and electric current. So what we're really talking about is charge buildup, charge transfer, and the interactions between the charges. Now, if you notice with these two words, electrostatics and electric current, so we're talking about interactions with electrons. That's what we have here. We've got a couple different equations. They look kind of scary based upon what's going on here, but it's not really all that bad. Notice the first one, F equals K, Q1, Q2 all over R squared. That's something called Coulomb's law. It deals with force interactions from stationary charges. That's the first thing we want to talk about because that's really by itself is the idea of electrostatics, the idea of electric fields. So what we're saying is if we have two charges, if I have a positive charge here and a negative charge here, we should realize that because they have negative charges, they have opposite charges, they're going to go ahead and have some type of force of interaction. The force of interaction in this case will indeed be an attractive force. Now, we'd see something like this. Now notice, I've drawn equal magnitudes with those relative forces. Third law states equal and opposite forces. So one pulls on one just as much as the other pulls on the other one. Even if we have one that's twice as large as the other one, meaning that this one is twice as positive, and however you want to dictate that, but these two forces would still be the same on both those two things. Now, the other part that we want to reference to this is the idea of an electric field. Electric fields surround particles. So if I have a positive charge like this, we have an electric field going like this. Excuse me. If you're going away from the positive, away from the positive. Okay? Electric fields are basically saying what would happen if you put a positive charge around something. Why is that so? Because early understandings thought that it was positive charges moving, not negative electrons. So if I put a positive charge there, it would be pushed away. We're trying to say this idea of an electric field. If I went ahead and I put a negative charge here, yes, I realized it would be pulled towards it. So that means that the force would be pulled this way, but my electric field would actually be in the opposite. Electric fields are what happens to positive test charge when introduced. Now going back to the idea of Coulomb's law, F is equal to K, Q1, Q2 all over R squared. K is a constant known as Coulomb's constant. Okay? Q1 and Q2, we use Q to abbreviate charges. The units per charge are coulombs. Now a coulomb is actually a very, very small, really, really big unit. So the charge of an electron is 1.6 times the negative 18th coulomb. So it's very, 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 very small relative to a very, very big unit. Okay? We find R is the distance in meters. So if we look at these things, if either one of these two charges increases, that means that the force will increase. If I look at that distance, as the distance between them increases, that force will decrease. It's not just going to decrease a little bit, it would decrease exponentially. If we were to look at a graph of force versus distance between these, when they're very, very close, we have a large force, and we'd see a very, very small force like this. This is something that we saw before, very similar to the idea of universal gravitation. Now, we want to focus it on these other equations that we have here. Voltage is the thing that makes charge move. Current, I, is the flow of charge. R is the resistance to that flow. We talked about a lot of different conceptual ideas, but we need to make sure that we stay conceptually sound on what those things mean. Voltage, V, is the thing that makes the charge move, I is the physical charge, and R is the resistance to that charge moving. So what we mean by that is we have a relationship, V equals IR, Ohm's law. We use that a couple different ways. We say that the voltage is equal to the product of current times resistance. Now, what is current? Current is flow of charge per time. Now, a big misconception is that if we have more charge moving, that means it's going to be happening faster. We got a delta T here, right? No, we have more charge moving. It does not mean that the delta T changes. So it's not that you turn something up in terms of something moving brighter, that the charges move faster. That's not what happens. It's just simply more charge moving. Now, we also find that power is equal to product of current times voltage. So more current and more voltage, you've got more power. Remember back from old ideas, power is also work per time. So we're talking about more energy transfer per time interval.
At this time, the last group of students that should be reporting to the Special Olympics Assembly in the auditorium are the returning volunteers. So at this point, cheerleaders, Silvoids crew, Olympic Village, track team members that signed up, new volunteers, and returning volunteers should all be reporting to the auditorium before your meeting. Thank you.
Power is work over time, so it's change in energy per time interval. So we can talk about the power output of a light bulb or something like that, or even deal with relative resistors. Now, also we get this other equation. Big R is equal to rho L over A. And maybe big L like that, or maybe a script L like that. That's talking about the resistance of a material or resistance of a wire. It's saying it's dependent on the resistivity, that's dependent on the material, that's the length, and that's the cross-sectional area. So before thick wires have less resistance than thin ones, long wires have more resistance than short ones. We can see the length, top area in the denominator. But we want to talk a bit more about these two things in terms of voltage, in terms of power and current stuff. So if we were to draw a simple circuit, there's a voltage source and there is a resistor like that. We say, okay, I have some voltage, it's going to have some resistance. Depending on what's going on, I can calculate some things. But we also get complicated things.
Also, all Key Club members that signed up to help in the Special Olympics should report to the auditorium right now as well. All Key Club members that signed up to help with the Special Olympics should be reporting to the auditorium at this time.
In looking at these two illustrations that I have in the bottom, these are two types of circuits. One, this is a reference to the series circuit. This one is referenced as a parallel circuit. Now, there are some things that we know. The total equivalent resistance in this one would be equal to the addition of the resistances. So we can do a bunch of different things with that. Then in the bottom here, we find that 1 over the total equivalent resistance would be equal to 1 over the inverses of those ideas. That's how we can find it. Again, we did many different problems like this within the class, but I just wanted to reference those ideas. Now, the other part we want to also talk about is the idea of current and voltage in each one of these circuits. In this case, we notice that's a single path, so all throughout we have a constant current. In this case, we have a branch there. So yes, we have some current here, and we're going to have some current here, and we have some current here. Now, what I'm just referencing is the idea of something that we talked about before, Kirik's rules. Kirik's rules state that in a loop, the total voltage sum is equal to 0. And we also talked about the idea of a junction rule. The current in is equal to current out. Now, junction rule can be seen in the bottom illustration, and in the top we see that it's the loop rule, that the voltage increase minus the voltage drops here would all be equal to 0. Basically, it's a reiteration of the conservation of energy. If we look at the bottom one, how we have a junction here and a junction here. Notice I have some current, there's some current in this top part, some current in the bottom part. The summation of those two currents would be equal to the current going in, which would be the same as that going out, which is not the conservation of energy, rather it's the conservation of charge. Now, we looked at a lot of different problems with dealing with some things here. And I want to just kind of show a conceptual idea of what things would happen if we have a weird, unique circuit and some things that we could do. So, if we have a circuit and we have something like this, so let's say that's a resistor, like a light bulb. That's a resistor, like a light bulb. And that's a battery. And over here I have a switch. Now, in this series of questions I want to ask, I want to try to think about some predictions about what you think is going to happen here. Let's go ahead and make this R1, and let's make this R1, and we're going to make this voltage, just V. Okay? So in this case, R1 and R2, are indeed going to be equal. Okay? Equal in relative resistance. You say to yourself, okay, when I have it right now, could I go ahead and find an equation? Could I go ahead and find the total current in that circuit? Yeah, it's not that bad. We just use Ohm's law and think about it. If it's a series circuit like this, that means the total resistance would be equal to those two things added up. And if I said that R1 is equal to R2, how could I find that current? So, okay, well, V equals IR, Ohm's law. Again, I can do it for individual parts as well as the entire circuit. So what does that mean for us? Okay, so I have that voltage, right, would be equal to my current. The total resistance would be those two things added up. Notice, well, don't I have a weird bar here? Yeah, but that's still just a series circuit. So that would be R1 plus R2. Well, hey, I know those two things are equal, so I can do V is equal to I. We just make that 2R1, right? So V over 2R1 is equal to I. That wasn't super crazy to do in order to go ahead and write this out in terms within the problem. But let's say I go ahead and I close that switch. I do this. Now, here's something you want to think about. Now, electrons take the path of least resistance. They're lazy. They're trying not to go ahead and go through things that are difficult to move through. So rather than going through this branch, they're going to do something unique. they'll bypass that middle branch because that's the path of least resistance. So virtually no current will go through that middle branch. So what will happen to the current then? Well, if I was to go in and look at this outside loop like this, right? You say, well, how could I do that, right? I got a weird junction there. What could I use? Well, maybe you say to yourself, well, I don't know what I want to use. And I'm going to try to see what's going on with this exact idea. Let's use Kirika Rules. So if I use this bottom loop right now, and I say that the sum of the voltages in that whole loop is equal to 0, that means that my voltage there minus the voltage drop in R1 would have to be equal to 0. Okay, well, what is the voltage drop in R1? Well, that would be, I can rewrite that, right? So that would be the current in the circuit times resistance 1 would be equal to 0. That's really not that bad to look at and say, okay, well, that's simple. Why didn't I just do it like that? Well, because I have a loop and I have something weird going through there, I would want to state it as a loop in terms of loop rule junctions, a loop rule, a Kirchhoff rules, in order to show that I know exactly what's going on. So then just simply reiterating this and trying to solve for that current then, right? I get I is equal to, move some things around, it's V over R1. Say, oh man, that looks so kinds of weird. And you notice, hey, the current is indeed going to be greater in this case. How much? Double, because we're bypassing that bottom part. Now, you could also be asked to go in and say, oh, but what is the what's the power output on these things? And say, oh man, that sounds really, really difficult. Well, if I know that current, right? If I know that current, and I was trying to find the power output in R1 in this case, or the power output on R1 in that case, right? Say, well, power is equal to current times voltage. So I could go ahead and say power, oh, I know the current already. And in that case, cool. I was able to find the power outputs in both those cases, and once again showing that the power output in that one would indeed be double that. So you could say energy transfer in the one in which the middle resistor got bypassed would be twice as much in terms of energy transfer. Now, careful in terms of this because we're dealing with electricity, and we got energy forms into other different things in the system. So you could not appropriately say all of it would be transferred to light because heat and things are also given off in these types of ideas. As always, thanks for watching. I hope you enjoyed the series. Catch you in the next video. Thanks.